We need to memorize this one. We're going to memorize hydrochloric. And we're going to memorize sulfuric acid. Oxyacids are not named after the Hydroblankic method, but they're named for their polyatomic ion. If you look at your list of polyatomic ions, everybody get out your list of polyatomic ions. You can choose any one, and you can look at the charge on that polyatomic ion, and based on that charge, that's how the number of hydrogen ions, protons, that you could add to it. So, phosphate, what's the charge on the phosphate ion? 3 minus. So you can put 3 hydrogens on there and make an acid out of it. You see that? So another one, SO3. What's the charge on this ion? 2 minus. So you can put 2 hydrogens on it and make an acid out of it, right? All of your polyatomic ions can do that, and that's where we get our oxyacids from. And the way you name an oxyacid is always based on that polyatomic acid, or polyatomic ion. So what's the polyatomic ion in sulfuric acid? Sulfate. Sulfate. All right? And what we're looking at here is the suffix for sulfate. If it ends in -ate, then we change it to sulfuric. It ends in -ic. The acid's name ends in -ic. All right? So here's another example. CO3. There's 2 hydrogens on there because the carbonate ion has a +2 charge, or -2 charge. So here's an acid. The name of the polyatomic ion is carbonate. So the name of the acid is what? Carbonic. Carbonic. All right, carbonic acid. Okay? So, again, this is carbonate ion, and we take the -ate and change it to -ic, and we call it carbonic acid. Now, it's not hydrocarbonic, it's not hydrosulfuric here, oxyacids. Just name the polyatomic ion with a suffix, and then call it acid. If the suffix is not -ic, ate, carbonate, what are other suffixes on there that you see? Ite. Ite. Suffixes that end in ite, ite, the acid's name is going to be end in ous. So can you give me a polyatomic ion whose suffix is ite? Nitrite, which is NO2, right? This is the nitrite ion. How many hydrogens should go with this nitrite ion? How do we know? The charge. What is the charge on the nitrite ion? Is it on your list there? It's not on your? It is, hooray. -1. So HNO2 is what kind of acid? Nitrous acid. Nitrous acid. Okay? So, simplified, and this is something I've inscribed at the headboard of my bed so that every time I wake up I see this, but ite goes to ic, and, no, 8 goes to ic, sorry. 8 goes to ic, ite goes to us. Right? What does this mean? If the polyatomic ion ends in -ate, the acid is ic. If the polyatomic ion ends in ite, the acid is us. Now, we don't really have to remember that, because what I've asked you to remember, which will serve you fine, is the name of this acid, right? If you remember that that's sulfuric acid, you'll always have your polyatomic ions to go back and say that's sulfate, and then you'll remember 8 goes to ic, and the other one must go to us. Okay? So let's see if we can practice naming some acids now. Which one is not supposed to be named following the Hydroblankic method here? C. C. Very good. What's A? What's the acid A? Hydrochloric. That's one that we want to have memorized, right? What's the second acid there? Hydrosulfuric. Good. The third one? Nitrous acid or nitric acid? How do you know? All right, NO3, we look at the polyatomic ions. What's the name of the NO3 ion? 8, nitrate. 8 goes to ic. Nitric acid. What's D? Hydrofluoric acid. Very good. Now, we also want to have a conversation about strong acids. Now, we talked about this before. What does it mean to be a strong acid? It dissociates fully. Strong acids, strong electrolytes, strong bases are strong because of their degree of dissociation. Right? That's what strength means. Okay? So, when we talk about, let me see here, I'm going to pass around a roll. When we talk about something like a weak acid, here are the rolls. No. There they are. All right. When we talk about a weak acid or a weak electrolyte, it means it only dissociates partially. And when we say partially, it depends because there's different kinds of weak acids. But for example, if you had 10,000 molecules of this acid and it was a weak acid, on average, 1 out of every 10,000 would probably be dissociated at any given time. Okay? So that's what we're talking about when we're talking about weak acids. Right? So strong acids, completely dissociated. And there's only 7 strong acids. Which slide talks about the strong acids? Do you guys see that slide? Let's see. There it was. Slide 30 talks about your strong acids. Okay? And the strong acids here are HCl, HBr, and HI. Hydrochloric, hydrobromic, hydroiodic. Those are our binary strong acids. And then the other ones are H2SO4, sulfuric acid, HNO3, nitric acid, HClO4, perchloric acid, and HClO3, chloric acid. Chloric acid. Okay? These are our strong acids. And these you do need to begin to recognize. All right? They will always dissociate completely when they're in solution. So we need to begin to recognize our strong acids. And I don't know that HClO3 is on your slides there, so you might want to make sure you add that one in to slide 30. HClO3, chloric acid. Okay, so then, how about this? HNO2. What did we decide this name of this acid was? Nitrous acid. Very good. It's the nitrite ion, and ite goes to us. Nitrous acid. How about HClO4? HClO4? So we have to look at our polyatomic ion chart. Perchloric. Very good. Perchlorate ion, 8 goes to ic. Perchloric acid. HF. Hydrofluoric. HMNO4. All right, good. Permanganic. Permanganic acid. H2CO3. Carbonic acid. Carbonic acid. Good. Got that one. Oh, we didn't do that one. I could have done that one. All right. Now, we want to recognize how, or remember, how our acids and bases dissociate when they're placed in water. Okay? Let me show you, let me remind you again, the general dissociation of an acid. Right? If an acid looks like this, has a proton that it's going to give away, and just something else, right? What are the products of its dissociation if this is an acid? Okay, A minus is left and H plus. All right. And the definition of an acid is a molecular compound that when placed in water, it will dissociate to release the H plus ion. Right? That's what an acid is. Now, the definition of a base is a little less specific because there's two ways in which you can have a chemical behave as a base. One is where you have a metal like sodium and polyatomic ion, hydroxide ion. That compound, when it's placed into water, is soluble. How do I know that this compound is going to be soluble? What's the rule in my solubility tables? 1. Rule 1 says it's going to be soluble. Therefore, which says that all first group metals are always soluble, right? Therefore, when I put this into water, I'm going to get the hydroxide ion, right? That's the other side of a water molecule. Proton and a hydroxide ion come together to form a water molecule. So a base is a compound you put into water, and the hydroxide ion results. Now, there's another way that I can get a hydroxide ion in a solution, right? It is where you have some chemical, and usually it's a nitrogen, or has a nitrogen on it. R means whatever, something else. Some chemical interacting with water. And this chemical will pull a proton off and leave behind the hydroxide ion in solution. Okay? There's two ways that chemicals can behave as bases. And this scenario will almost always be a weak base, and so we draw a second arrow on there. A strong acid from a weak acid, you'll be able to recognize simply because it's one of those 7, it's a strong acid. Also, if it's a weak acid, it will generally have a second arrow. And if they say, what's the dissociation for this weak acid, you want to make sure you include the second arrow, right? Do we need to talk about what that second arrow means? Anybody want to talk about that? It means that this dissociates, but then it comes right back. And the amount of dissociation is very small compared to the amount of acid that's in solution, right? We said 1 in 8,000, 1 in 10,000 actually ever dissociates at any given moment. Yeah? This one here? So what I've done is I took Rn, right? And I'm taking a proton off of a water molecule. So this positively charged thing is going over to here. And when it goes there, that positive charge goes with it, right? And then what's left is these electrons. They come back onto this oxygen and end up with extra electrons all around and a negative charge. All right? And one thing that you'll notice is the sum of all of the charges on one side of the equation will always equal the sum of the charges on the other side, right? Okay? So, another way that we can draw acids dissociating, which you have to be familiar with, which I'm not a terrible fan of, is we include the water molecule. And when you include the water molecule, then this H plus that results is going to be piggybacking on a water molecule. Can you see the similarity between this dissociation and this one here? The only difference is this water molecule is the thing that ends up taking that H, and it becomes H3O+. Can you guys see that okay? And hopefully you've had a little practice working with those kinds of problems, so either one of these hopefully you'll be comfortable with. So did you get to write how methylamine will act as a base? Did you get to write that down on your slide? Who needs more time to answer this question up here? All right. So again, this is the one right here, right? It's acting as a weak base, so this is the one that we're going to try to be following here. So we have to show it interacting with water, right? We're going to show methylamine, CH3, NH2, plus water. Plus water. And then the product, we know it's a base, so one of the products has to be hydroxide ion. And the other product is the methylamine taking a proton away. Right? Did you get it, you think? Oh, okay. Well, this is kind of a reminder. This is how a strong base would dissociate. This is how a weak base behaves. It pulls a proton off of water and results in the rest of the water molecule, which is the hydroxide ion. So this one here is methylamine. It's acting as a weak base. So this is what we want to, how we want to write it doing. It has to look like that, where this is the methylamine interacting with water. And it's going to have the methylamine with an extra hydrogen and a positive charge and the hydroxide ion. Okay, who got that one? Raise your hand if you got that one. So we have methylamine interacting with the water, right? Yeah.
Does it matter like which hydrogen at the extra hydrogen? CH4 and H2.
Okay. It kind of does. It kind of does. And we don't really have time to go into it. The only thing is that carbon has 3 hydrogens on it in this compound, and nitrogen has 2 hydrogens. And carbon isn't going to be the one where the hydrogens are going to come on and off very easily. It's nitrogen. Now, there's no way that you would know that. So they would never give you like a multiple choice scenario where the hydrogen was either on the carbon or on the nitrogen. They would always have it be on the nitrogen, so it's not something that we have to be terribly keen about. But, yes, it does matter. Okay? This is methylamine. It's taken a proton. See that? It's got another one, and it's got a positive charge. You got it from this water molecule, so that's what's left over. Can you see how that works? And this will be a problem I can almost guarantee will be on your exam. This one and also on the final. It'll say, here's a compound. It's a weak base. Show how it acts as a weak base. So you have to be able to recognize that it interacts with water, takes a proton, and then leaves behind the hydroxide ion. Okay? All right, so how about nitrous acid acting as an acid? How is this going to act as an acid? Well, here are some examples. Nitrous acid, is it a strong acid or a weak acid? How do we know? Oh yeah, because it says. If we didn't have that to say it though, again, these are our only strong acids. So because it's not a strong acid, then it is a weak acid. Okay, so it's going to behave like a weak acid. Both of these are the same thing. Hopefully you can see that. If you can't, we have to have a conversation about that so that you can tell how these are the same. If you just write the answer like this for that weak acid, that's fine. If you write it like this, that's what you'll have to be familiar with. Okay, so again, we had our acid giving a proton to water. The double arrows, because it's a weak acid, I would have just written it like this, HNO2 going to hydrogen ion and the nitrite ion. There's the dissociation that I would be interested in seeing. Anybody want to talk about that one? Okay, what about the chloric acid? Is that one easy? Anybody need more time on this one? No? So, same thing. This time we have a single arrow and HClO3 dissociating to H plus and the chlorate ion. That's enough of a dissociation, in my opinion. How about strontium hydroxide? If it's supposed to be a strong base, what is it going to look like? So write down the two ions that we have. Right, we're just writing the dissociation of this compound, the ionization of this compound. Okay, see how this is a strong base. See the strong base example up there, the top one to the right side?
It only has one arrow,
It only has one arrow, and we don't need a water molecule, right? No. The top one on the right there, that's what happens there. We just show the dissociation. Right? Okay, so in this dissociation, hopefully, the sticky points, right? You got a +2 charge here. Got to make sure you have that. And you got to make sure you had 2 here for the number of hydroxide ions. Who got those ones right? Anybody want to tell us you got it right? Not a single soul. Okay. Should we try a couple others? Okay, I'm going to erase these now. All right. Need water? Because, well, what would the water molecule be doing? I mean, there are water molecules. So you just have strontium hydroxide here, right? And you want to show what happens when it's placed in water. If you put water up here, this is an ionic compound that's soluble in water, so it's going to dissociate into strontium ion, and you're going to have 2 hydroxide ions. And that's that. And then, you're just going to have to write water again there, right? I mean, the water is involved in that these end up being aqueous, right? But there's no place that we actually draw the water molecule around it. Does that make sense? For a weak acid, like here's an example of a weak acid, H3PO4 is a weak acid. Its dissociation, H and H2PO4 minus, to me that's a lot simpler. And when you throw the water molecule in and say, okay, H3PO4 combines with the water molecule, I mean, what is the water molecule doing? It's not doing anything. It's just it's allowing I don't know. The hydrogen's going onto the water molecule. But it's not there permanently. So it's kind of the same scenario over there. Water molecules are interacting with the ions, but people want you to be familiar with this part. That's why I don't like this, because it H2PO4 minus. Because it makes you think that you need to have the water molecule here with the proton, but why don't you have the water molecule here with these ions? So, something you just kind of have to be ready for. All right, so let's practice one, okay? I'm not going to tell you whether or not it's a strong acid, a weak acid, strong base, or a weak base. I'll leave that up there, and we'll see if you can determine which one it is. Essentially, for all of these, we're going to write how these interact with water, or write the equation. Yeah, that's it. Write the equation for how the following chemicals interact with water. Okay? So, here we go. HC2H3O2, HBr, CH3CH2NH. This one I will tell you is a weak base. BaOH 2, KOH, FeOH 2. All right, so we have some practice problems here. We're going to write how all of these interact with water. I'll throw a couple others over here too. Okay. How do these chemicals interact with water? When placed in water, what do they do? That was right. What happened?
That was right. Okay.
Was that a positive charge on that hydrogen?
It was negative.
But it's easy to turn into a positive charge, right?
I have a question.
Mm-hmm.
On those, I don't really remember how you worded it, but I'll explain it. But I don't understand it because you said when I think that the base goes.
You think that the base goes what?
When on the board when the base dissociates,
Mm-hmm.
what determines the positive charge again?
Oh, strontium? How did we know strontium has a positive too?
Uh-huh.
Because of its location on the periodic table.
Or I don't know if it was that one. I think it was one of the top two ones where you were talking about on the test. We need to know if you were given a weak base that something with a proton, but I can't remember what you said.
Well, we just need to know that if they say this is a weak base, what do bases do? Weak bases. What do weak bases do? Weak bases take protons from water. They take a single proton from water, and they leave behind the hydroxide ion.
Okay.
So you have to be able to draw that in a chemical equation. So you draw that weak base interacting with water, and then show the products where it's taken a proton and left behind the hydroxide ion.
Okay. I have another question.
Mm-hmm.
I clicked on here, but how do we determine the difference between bases and acids?
An acid and a base?
Yeah.
An acid is a chemical that when placed in water, it will release a hydrogen ion.
Yeah, but
So like looking at it chemically, how do you know?
yeah.
Usually an acid will start with a hydrogen. That's nice.
Okay.
So up here, all of our 8 we have, there's only 2 that start with hydrogens, and those are the only 2 that are acids.
Okay. Okay, so thank you.
Okay, so HC2H3O2. Does anybody know what this chemical is? What is this? Acetate ion. Therefore, what kind of acid is it? So do we know that this is an acid simply by looking at it?
No.
Okay, the hydrogen in front should give it away. Right? When there's a hydrogen in front, that's one way to know that it's an acid. The other way is because you can see the polyatomic ion there. You can see the polyatomic ion, and then it's a hydrogen attached to a polyatomic ion. So that's the other way you can tell. What's the name of the polyatomic ion here? Acetate ion, so the acid's name is, ate goes to what? Ic. So it's acetic acid. So because I know that this is an acid, then I know that what's going to be on the product side? A hydrogen ion, right? That's what acids do. They go into water and they release the hydrogen ion. This one, is this a hydrogen ion? Or sorry, is this an acid? Yes. So I'm giving you a little hint. I know that on the right it has to be a hydrogen ion. Is this a base? Yes, it said weak base. So I'm giving you a little help. I know that on the right there's going to be a hydroxide ion. Is this a base? All right. So then if it is a base, I know that there's going to be a hydroxide ion on the right. Is this a base? Is this a base? Okay?
So how do you know not to add water like that last one?
Okay. So there's two ways. Well, let's see how far we can get on these first. Who's gotten this one done? Anybody worked on this one yet? What's my other dissociative product here? C2H3O2 minus. Do you see it? It was just the proton and the acetate ion. Yeah. Well, we have to be ready to do that because people expect us to recognize that. If we were adding water, what would change? That's right. We'd have HC2H3O2, add in a water molecule, and all that water molecule does is it holds on to that proton for us, right? So either of those would be, whoops, with a negative charge. Either of those would be okay. How about this one? What's the other dissociative product when I put hydrobromic acid into solution? The bromide ion? Do you want me to write it with water, or can you see what it would be like? Yeah, HBr. If I wanted to have this other form of writing it, then instead of H+, I would write H3O+, and the bromide ion. Okay, how about the weak acid? What does the weak acid do? The weak acid we can't write without water, right? You need to have water. You have to have water. Because look, there's no hydroxide ion in this thing. If this is acting like a base, that means hydroxide ion has to be resulting. Where did the hydroxide ion come from? It came from this thing interacting with the water. How do I get from here to there? What have I had to have done? Yeah, yes, that's right. I have to remove a hydrogen from water. Where does that hydrogen go? It goes to the NH, right? So CH3, CH2, NH2. And then I have to put a plus charge on there, right? Because when it takes that hydrogen ion, that's a hydrogen ion, H plus charge, it picks up that plus charge. This one's a weak acid. Barium hydroxide. Now somebody told me that this was going to have a hydroxide ion down here because, I don't know, how did you know barium hydroxide was a base? I heard somebody say, or I think we decided it was a base. How do we know though? Okay, so it's not an acid, right? That's one way of thinking about it, but this isn't a base and there's no hydrogen in front. What's the definition of a base? You put it in water and what? You put it in water, because this doesn't dissociate, does it? This isn't dissociating, you see it? So we have to have our definition encompass weak bases as well. The definition is you put it in water and the hydroxide ion results somehow. All right? And the hydroxide ion has resulted here for this weak base. See it? How is the hydroxide ion going to result here? This chemical has to dissociate. It's right there, so there it is. But if it doesn't dissociate, then it won't be a base. True? How do we know if it's going to dissociate or not? Our rules. Can anybody give me a rule to verify that barium hydroxide will dissociate? Is barium group 1? No, but number 5, is barium an exception in number 5? Excellent. So that's how we know. All right, so let's finish up this dissociation. What else goes here? Barium ion. What's the charge on a barium ion? +2. Very good. Am I missing anything here? Yeah, we need 2 of these hydroxide ions. Okay, because that's what this says here. We had 2 hydroxide ions.
So that would be a strong base.
Yes, that's a strong base. Strong base is a chemical that, to get the hydroxide ion, it was just from dissociation of some ionic compound. How about KOH? What are we missing up here? Do we know that KOH is going to be a strong acid, or base, first of all? I just drew this in here because somebody told me. What rule? 1. 1 says that any metal that's the first group is going to always dissociate. Sorry, any salt that contains a metal from the first group is always going to dissociate. Very good. So what's the other thing that we have to write up here to show it how it dissociates? Just the potassium ion. So there's that dissociation. How about this one down here? What are our ions that are going to result when this is placed into water? Iron. Okay, this is a base and this is not a base, right? How can you tell it's not a base? It won't dissociate. Rule 5 does not have iron in there. Hydroxide ions are generally, salts containing hydroxide ion are generally insoluble. So that is not going to dissociate. So that's it. You put that into water and that's it, that's all. It's just going to make a pile of that stuff on the ground. How about this one? Is this an acid or a base? Or is it not a base? It's not, is it? It's not a base and it's not an acid either, right? But we can show how it's going to dissociate in water. How will it dissociate in water? Or will it? Will it dissociate in water? How do we know? Rule 4 says that sulfates are generally soluble, and Rule 1 says that potassium ion always going to dissociate. Okay, so I'm going to get potassium ions, and I can see I'm going to get sulfate ions. Am I done? 2 potassium ions, right? Excellent. Nickel 2 nitrate. Where'd you get your nickel 2 nitrate? Costco. Cool. So what are the dissociative products of your nickel 2 nitrate? What are the dissociative products? Looks like we're going to have what kind of an ion? A nickel ion? And the NO3 ion? What are the charge on these things? Nickel is a positive. A 2 in front of it like this? We're feeling it, huh? How did we know there was 2 nickels? The 2 means there's 2 nitrates, right? I think the 2 is supposed to go there. I don't think we got 2 nickels. The charge is a +2. Charge is a +2. Very good. And the nitrate, what's the charge on the nitrate? -1, right? A singly minus charge. Are we getting it? Yeah.
So how do we know that, or like why isn't K2SO4 an acid or a base?
Okay, what's the definition of an acid? What? No. What's the definition of an acid? A chemical that you put in water and it dissociates, and this is the definition of an acid. You put it in water, it dissociates, and one of those dissociative products is the hydrogen ion. right? So I put this into solution, it dissociates. So we got 2 for 3, right? Something that dissociates in water. But the third thing is what? It leaches the hydrogen ion. So there's no hydrogen ions here, so that's not an acid. A base, what's the definition of base? You put it into water and you get an OH ion, right? Now we can't say that the definition of a base is you put it into water and it dissociates into OH. Why can't we say that? Yeah, because some bases behave differently, like this one here, right? If you put a chemical into water and it dissociates, and one of the things, a hydroxide ion, it is a base. But you can also put chemicals into water and they'll just pull protons off of hydrogens, and that will result in the hydroxide ion. So it's not always from dissociation. Wow! I feel like we could do like 20 more of these. It's still kind of stuck, huh? Should we try some more?
Wait, so what if you K2SO4 plus H2O?
What's that?
K2SO4 plus H2O.
Okay.